random variables. So this just could be data I collected, and I've got data 1 or data and data 2. And so if for a QQ plot, if I want to know if these come from the same distribution, if I were to plot sort data by sort data 2, you see how there's this S-shaped curve. That would indicate they're different distributions, which I could have seen by saying his data is data 2, and by looking at this I can probably guess that these are different because I've collected enough observations. But if I hadn't collected that many observations, it might be harder to tell, and I might want stronger evidence. But these look different here, and they look different according to the QQ plot. But I can also, instead of using data, plotting data against one another, I could plot against the quantiles of the normal distribution. And so here I can take data sampled from a normal distribution and plot it against the quantiles of the normal, and it's not a perfectly straight line, but it's roughly straight. If I plot it against the quantiles of uniform, we see that same S-shaped curve. And now if I took a uniform and plotted against a normal, you see like an S-shaped curve in the opposite direction. But a uniform plotted against a uniform looks pretty flat. So by looking at these, you can, this is a good diagnostic to see whether your distribution is, to a first approximation, fits the assumptions of the distribution you're assuming. So along with, because you might do this, you might find a histogram and you can't really tell if it's normal or not. It looks sort of reasonably symmetric, or maybe it looks asymmetric, but you want to know, is it really asymmetric enough? And doing this can help you understand whether, not only whether your distribution is reasonable, but maybe you do a transformation or outlier removal, then you can check if it's better. You can use this to help understand if you transform your data into something that would work. I sent you this data file, right?
Yeah.
Yeah.
Okay, load that data file. And tell me what you think about its distribution. Oh, this is like the way of making a QQ plot by hand. There's a QQ plot function and there's a QQ norm function. And the QQ norm is essentially the only one you ever use. So if you do QQ norm data, it will create that same plot. And it looks a little nicer than the one I have. And if I do QQ norm data, so here's against the normally sampled data, and you can see it's flat. So here's just actually one subject from the data you used on the test exam.
So what I understand is, so first we actually use certain parameters which we design on certain terms, and to see if our data fits either of these distributions. And then we could use the the math or stats for that particular distribution. And
yeah. So what I just want you to do here is take a look at the RT column of this data and I've done this now. We've looked at the distribution for data that we know what the distribution is, because I generated it. But what about this distribution? Can we tell if this data distribution fits our model? And so the first thing to do is look at a histogram of it. So can you do that? And then you can use QQ norm on it as well. You don't have to do this QQ plot by hand, but I wanted to show you how it's made so you have some understanding of what it's about. So if I do a histogram, I can see that it's highly skewed. In fact, there's 1 or 2 points that are really long. That might be, most of the time people responded in less than a second, or in not too much more than a second. And then it's got this long tail. And so the question would be, would this cause problems if we tried to model this with a normal distribution? And what are the violations? So the violations are that it's not symmetric. But the violations may also be that whatever's going on here is probably different than what's going on here. What's going on here was they were checking their texts for 5 seconds and then they made the response. Or they're daydreaming. And maybe that's not what I'm interested in here. So
do we change this to fit the normal? Is it okay?
We're not doing that yet. So all we're doing is trying to figure out how well this conforms to the normal distribution. So our our histogram, it doesn't look great, and if I do a QQ norm, this is what it looks like. So this is not a straight line, and it's flat here and then it jumps up, which is just an indication of a right skewed distribution with a long tail. So this would be evidence against the normal distribution being a reasonable model of this. And maybe, if I got rid of these 2 points here, it would be better. Or maybe there's some transform. And so it's really common, if you have response time data, to do a transform like a logarithmic transform. So you take the log of it, and 90% of the time, response time data conform much better to the normal distribution when you take the log of them. So here is what happens when I take the log. And in fact, it's not bad. I would say it's still a little skewed, but it's really not bad. Especially if we focus on the 90% of the data in the middle or the 80% in the middle. There's still kind of a long tail here. What does this look like if I do QQ norm here? Well, it's flatter, but it's still not great. So then I might think outlier removal. So maybe I'll do data 2 is equal to data RT less than 5,000. So if they weren't able to make it in, if they weren't able to respond in 5 seconds, I'm just going to throw them out. So I can do a hist of data 2. And again, this is going to have a long tail. Hist.
3,000.
Well, I don't know if I want to. I don't know. I mean, there are procedures that you can use, but this is, that might be the right thing. It might not be. But let's see what happens if I throw that out. Now, if I take the log of it, I got rid of some of that, and now. But here's the real test: Q norm of log data 2. It's getting better. So the question would be, maybe I try remove. Maybe I still want to remove stuff. Maybe this isn't a terrible model. I mean, it's not the right model, but maybe it's not terrible. Maybe it's good enough that I could use it for whatever case I'm thinking of. And it's completely typical for people when they do experiments with a lot of response time to do data trimming, removing outliers like this. It's just part of the process that experimental psychologists undergo in order to make sure that they're not being, make sure that these outliers are not getting into the picture because they're so far out there, they can have large influences on your conclusions. So you want to make sure that whatever you're concluding is not just about a couple trials that might not have even been about the process you cared about, but are really about where most of the trials belong. So, okay, so that's just sort of an example of using QQ norm on data. I probably, if I really cared about this, whether or not this was normal, this is still a little bowed to convince me that it's normal, and I might try other transformations that help more. Like I might, there's other transformations, but I might do something like, if I do something like that, or I don't know, do a double log transform or something. I could probably transform it into a space that's essentially normal. Whether or not that really matters is up, depends on the particular application and what type of inference I'm trying to make. Okay, so those are QQ plots, which help us understand whether our data match